Okay, Unit 6. This is the formation of basically planetary systems, but our solar system, of course, is one of these. And if you look at this picture, we actually think we have a picture of a relatively early forming planetary system. We have what's called the proto-sun. The sun is actually heating up because of concentration, because of friction, because of basically friction. And you can see it's actually um, causing some light to go out. You can see these planetary objects are actually causing shadows. You can see banding going around where planets will form. Um, and then eventually this will actually get hot enough, 10 million degrees Celsius, where nuclear fusion will kick in. Hydrogen will actually get fused into helium. That produces a little bit of a lost mass, and that mass goes into E is equal to mc squared and produces a bunch of energy, and that's basically what powers stars. So we go from a proto-sun and protoplanets to a sun and planets, all through accretion of planetesimals and nuclear fusion. Okay, here is the Horsehead Nebula, and you can start seeing some of these kind of concentrations. I hate that when that happens. Okay, so now after the phone call, this is the Horsehead Nebula. It's in the Orion Nebula, or excuse me, Orion constellation. It's right next to the belt, and I'll actually have a video here you can watch. I'll put it in the comment for the video. But this is the Horsehead Nebula, and you can see there are some concentration areas in it, and this is where we actually think the planetary nebula are actually forming. You can see stars that are actually in front, and then some of those stars probably behind. This is probably not one in the nebula, it's probably one in front of the nebula, just like the rest of these are. But we think these areas that you can see as like delineation, or you can see as little globules, are probably planetary nebula. We just have to live long enough to watch them form. And then the next image, somebody was actually having fun looking at planetary nebula and made, I'm not even sure what this is, but what he typed in is that he saw the Helix Nebula and actually saw how closely they resembled eyes and wanted to compose a face based on other nebula. So he used Ryan, he used Shapeless Nebula, he used the butterfly for the bow tie, the helix for the eyes, the hand of God that he flipped for the hands of God, and then Thor's Helmet Nebula. Actually, I think it's there. This is probably the Shapeless or the Orion Nebula. Don't know what, but I thought it was worthy. Okay. So what do you think? How many stars are there in the solar system? Was the solar system created in a direct result of the formation of the universe? How long was the Earth, or how long has the Earth existed? Is Pluto always the farthest planet? What typical shape do moons have? And have any Earth-like planets been discovered orbiting stars like ours? We will discover how the solar system formed, why environments in the early solar system were very violent and much more than today, how planets are grouped, which we've already talked about. Astronomers characterize each planet in terms of a personality, and how the moons throughout the solar system formed, and the debris of the solar system and what was it made, as well as planets have been observed around other stars. Oh, and I guess there's one more. Newly formed star and planet system are being observed. Okay, so way back when, the lightest and simplest of all the elements, hydrogen and helium, these are the most abundant in the universe. Hydrogen makes up well more than 90%, and with helium, we're talking 99.9% of the known universe. So all the rest of the periodic table is a very, very small amount. And these were all created by the Big Bang. Heavier elements like iron and silicon are actually created by exploding stars. As you can see, I think this is the Crab Nebula. Basically, we have thermonuclear reactions going on. We have the fusion of heavier elements, and the bigger this explosion, the heavier elements that are created. So we think our sun will probably be able to make maybe up to carbon, which is still on that second line of the periodic table. And we know we have heavier elements like gold and lead and platinum, and then all those that are very short-lived. But we had to have really big stars to fuse those. So here are two different types of nebula. We have the formation of planetary nebula, and we also have supernova explosions. Planetary nebula are caused by exploding stars like this. This would be planetary nebula, and then we also get some exploding very, very, very violently, creating the heavier elements. And we are all children of the stars. Okay, great clouds of gas ejected out from stars. This is actually in the belt of this. Here's the Horsehead Nebula. This is in the belt of Orion. It's located right there, and we're actually looking at young stars, and we're looking at planetary. We think planetary nebula forming, and what will happen is the star will form, and then the rest of this material will coalesce and actually make planets. So we actually think we have these things going on here. And I will show you in class the Horsehead Nebula, and I will also post this in the comment for the video. Okay, solar system formation. It's called the nebular hypothesis. We start with a nebula, and as you can see, it condenses, it starts to spin, it flattens out, it forms a protostar, and actually these bands, which will eventually get coalesced into planets, and then we'll get a star, single solitary star, and we'll get planets orbiting like we have in our solar system. Here's a kid's view of it, same sort of thing. It comes together, starts to spin, flattens out, we get a star, and we get planets. Okay, here's our first drawing. I'd like you to draw these as well as write the description. So first thing, the solar system begins to spin. We're showing this one as a counterclockwise spin because this is the way our planets revolve around the sun, and this is all due to gravity. The condensation from the center gets hotter because of friction, and it starts to become a protostar. It's still not a star. It's called a protostar because it's before a star, like a prototype. And then the disk flattens, it's still spinning, protostar begins to shine, and then we get to this picture. Again, we're drawing and writing. Rising temperature of the sun starts to remove gas from the inner regions, cleans out, and the dust starts forming as these debris clouds. And then eventually almost all the remaining gas and dust, all the debris, coalesces into these larger objects known as planets that we recognize today. Okay, here are a couple of pictures of a planetary disk around a star where we think that we'll also start getting this. And to give you some idea, here's another one which we blotched out to blotch out the sun or the star in the middle because it was so bright. You can see this planetary disk out here, and this is the size of Pluto's orbit. So this is much larger than our solar system. I'm pretty sure this one is too. So you can look at young star systems developing today. The planets orbiting these stars are formed from the surrounding gas disks of gas and dust, and these protoplanet disks are called proploids. So these are proploid areas. Here's a planetary nebula montage. These are all planetary nebula. You can see they come in different colors, and these are probably all false color to actually show you definition of things. But you can start seeing some really neat shapes, different shapes. Some things that are amorphous, maybe don't have a shape, and then some things that are very circular. And remember, they're circular in 3D. We only see this because we're looking through stuff that's toward us as well as stuff that's away from us and stuff that's in the middle. The section in the middle looks not as thick because we're looking through just the section that's in front of us toward that star, and you can see that there is a star in the middle of that one, so pretty easy to see. I don't think I'm going to get through. I was hoping I could do this in one video, but I'm already over 9 minutes. I'm going to take a couple more slides, then I'll call this one A, and then we'll do B later. So here's a picture of Kepler-69 called the habitable zone. Because of the brightness and the heat of the star, anything in this green area would be having water at all three phases, If other conditions are right, you can see Venus is in our habitable zone, but not as habitable because of its atmosphere, sulfuric acid, high surface pressure and temperature. And we also have Mars in the habitable zone, probably better in the habitable zone, even though it doesn't really have a very thin or has a very thin atmosphere, about 1% of the Earth's, so it can't actually hold liquid water on the planet, although its temperatures would allow liquid as well as gaseous water and frozen water like this one right here, our planet. So you can see it has a non-habitable planet, but it also has a habitable planet, probably very similar to Venus. So if all of the conditions are correct, we may actually have other living planets, although it's much larger than the Earth. It's probably about the size of, or the mass of Jupiter. We have the Goldilocks principle, which basically means we have a hot area close to the sun, we have a cold area really far from the sun, and then we have the center section. But the temperature is going to actually be really important in this next phase. So here's our proto-sun, and we have areas that are close to the sun, very hot, and because of that, the coalescing grain sizes, the coalescing planetesimals, the things that are actually going to form the planets are going to be made of different material than the material way the heck out here. So within this disk that surrounds the proto-sun, we have solid grains that collide. These do something called accretion. They come together. This is accretion. And they actually form what are called planetesimals, small planetary objects. And they can be smaller than a kilometer or larger than a kilometer, but certainly not the size of a planet. These planetesimals are actually close to the sun. What we get are what are called terrestrial planets, and this is when the temperatures are actually cool enough that rock and metal starts to solidify. So these planetesimals, these dust grains, and these planetesimals are made out of rock and metal material, and as they come together, they actually cause friction, and that of course would take the metals, the more dense material, and they would go in toward the center, and the rock material would float out. And that would be true even when these planetesimals come together. If it happens farther out, we're not going to have rock and metal, or at least not in as high a concentration. What we're going to get is we're going to get concentration of gases like hydrogen and helium and methane, and they're going to make what are called the Jovian planets because they're accreted material or condensed gases. So basically what we're doing is we're getting gases to be the dust grains and gases to be the protoplanets, and then the planets themselves are more like gases and ices. Here's a picture of the formation of the universe. We have comets, and notice that the tail is coming away from the sun, which some of you are not getting when you're doing that test. I really thought that actually came through pretty clear in the video. And then we have planetesimals actually forming, and they coalesce, run together due to gravity, and then they make larger and larger planets. And then we get the terrestrials because they're in the warmer zone where we only get the condensation of rocks and metals. We don't get any ices out here because it's still the gases are too high energy and they can't come together. They only form way the heck out here. So these little blobs are more like gases and ices, and they're going to form more the Jovian. So we have the terrestrial type and we have the Jovian type. Computer animation, where we actually get these, we have 100 planetesimals that are going around. That's what the blue lines are, their orbits, and you can see that they coalesce. And then eventually, within 441 million years, they only have 4 planets that go. So if we threw in more planetesimals, we would get more planets. But basically, we get this accretion of these planetesimals, making larger and larger planets, fewer and fewer objects, until we finally clean out our orbits and pretty much have what we see today. And I'll show you this, or I'll put this video in the comments as well. Okay, the last slide I'm going to show, because we're actually at 14 minutes now, almost. This is our solar system, and you can see, if you remember that virtual solar system we did, we have these planets really close, then we have planets farther away. So as viewed from above, all the planets move in a counterclockwise direction. And it sort of says we all came out of the same nebula, and they almost all go within 7 degrees except for Pluto. And remember, Pluto is 17 degrees off the ecliptic. And between 1999, excuse me, 1979 and 1999, Pluto was closer to the sun than Neptune. It actually was much farther away than Neptune's orbit, but it actually was closer to the sun than Neptune. So when I was actually started to teach, which was probably when Pluto was about right there, we actually about right there. What happened was Pluto was the closest planet, or was closer to Neptune. So Neptune was the farthest planet until 17 years ago. And now Pluto, in its 270 plus year orbit, will go around, and then eventually it'll come back and it will be inside, but again, way the heck down here. Okay, I'm going to call it quits there, even though that's not, in terms of information, not the best bet, but this is 15 plus minutes. Okay, so we're going to call that one 6A. Thank you.